In this lesson, we will see that there is an alternative method of bringing an out-of-limit centre of gravity into limits. This time, mass will be added to or removed from the aeroplane in order to correct the centre of gravity. The adding or removing of mass from the aeroplane can take the form of either cargo or passengers, but sometimes operators will use mass called ballast, which is a mass that stands alone. This example shows an aeroplane with a problem, whose centre of gravity is forward of limits for takeoff. This can be corrected before flight using the method of adding or removing mass. By adding or removing a mass, the moments about the datum are changed. Assuming equilibrium to be maintained, the original total moment plus or minus the moment of the added or removed mass must equal the new total moment. This can be represented by the formula new moment equals old moment plus or minus change in moment. Another way of looking at this is to say that the finish equals the start plus or minus the change. The plus and minus is explained by using a plus sign when mass is added and a minus sign when mass is removed. Using the basic new moment equals old moment plus or minus change in moment, we can proceed in constructing the detailed parts of the formula. First of all, let big M represent the original mass of the aeroplane. Now let little m represent the mass to be added or removed. Next, let x represent the original centre of gravity distance from datum. The next step is to let y represent the final centre of gravity distance from the datum after the mass has been added or removed. To complete the formula, let z represent the distance from the datum that the mass has to be added or removed. It is conventional to use the centre of a hole to represent its distance from the datum, hence the term centroid. Finally, when adding or removing mass to correct the centre of gravity, use the appropriate one of the two formulae shown on screen. We can now work through an example for correcting the centre of gravity, which is aft of the aft centre of gravity limit, by using the adding or removing mass formula. This example requires finding out how much mass, little m, must be added to the forward cargo hold A, 4 meters forward of datum, to bring the centre of gravity onto the aft limit, 0.8 of a metre aft of datum. The mass is 5,000 kilograms, and the original centre of gravity is 1 metre aft of datum. In this instance, all of the details are given on a representative aeroplane on screen, and the first step is to apportion the data to the key letters used in the formula. Write down the formula and make sure that the change in moment is in the correct sense. In this case, it is a positive because we are adding mass. We are now ready to place the known values into the first line of the formula. On the left side of the equation, put in brackets the original mass big M, 5,000, plus the mass to add, little m. Multiply the brackets by final centre of gravity distance y, 0.8. On the right-hand side of the equation, put in brackets 5,000 times original centre of gravity distance x, 1. Add, in brackets, little m times distance from datum z, minus 4. Resolving the first line will now give us, on the left side of the equation, 4,000 plus 0.8 little m, and on the right side, 5,000 minus 4 little m. Bring all of the values for little m, 0.8 plus 4, to the left side and the whole numbers, 5,000 minus 4,000, to the right side. On the left hand of the equation is 4.8 little m equal to 1,000 on the right side. The value of little m is achieved by dividing 1,000 by 4.8, resulting in 208.33 being the mass in kilograms that has to be added to the forward hold A to bring the centre of gravity onto the aft limit. Here is another example of adjusting the centre of gravity to bring it into limits by removing mass. Once again, we will use the formula, but this time, however, there is no picture accompanying the question, and it is advisable to draw a simple line sketch to represent the situation. The sketch contains all of the data in question, including the unknown mass to be removed, little m. Start by giving the values from the question to the letters used in the formula, big M, X, Y, Z, with the unknown being little m. In order to solve this question, the formula must be written down, and in this case, for removing mass, new equals old minus change. We are now ready to substitute values into the first line of the formula. On the left side of the formula, put in brackets the original mass, big M, of 5,000 kilograms, then minus little m, the unknown. Multiply the brackets by y, the final centre of gravity distance, which is 1. On the right of the equation, in brackets, multiply big M, 5,000, by the original centre of gravity x, 0.8, and then minus, in brackets, little m, multiplied by distance mass to be removed, z, minus 3. Multiplying the brackets on the left of the equation gives 5,000 minus 1 little m, and on the right side gives 4,000 plus 3 little m. Note, multiplying the two minus signs on the right-hand side produces a plus. Rearranging gives minus 1 little m and minus 3 little m on the left side and the whole numbers on the right-hand side, 4,000 minus 5,000. Resolving little m and whole numbers results in minus 4 little m equal to minus 1,000. Solving for the value of little m by dividing minus 1,000 by minus 4 gives 250 kilograms, being the amount of mass required to be removed from the forward hold to bring the centre of gravity onto the forward limit, 1 metre from datum. In this lesson, we have learnt the formula to use when resolving an out-of-limit centre of gravity problem by either adding or removing mass from the aeroplane. It is always advisable to draw a simple line sketch if the problem is presented without a picture. In order to solve this type of problem, the operator may add or remove a mass which is known as ballast, which is a mass independent of the cargo, passengers or freight, carried on the aeroplane.